My dear students, you are welcome to another session of biochemical pharmacology, page 407. This is the lecture 2 in the series, and the topic is chemistry, classification, and nomenclature of drugs. Dear students, as usual, let me take you down the learning objectives of this subject topic for today. At the end of this lecture, it will be expected that you will understand the concept of drug kinetics, be able to explain the concept of drug dynamics, understand drug structure and reactivity, be able to explain the bonding in drug-target interaction, and explain the basis of drug classifications and nomenclature. Now let's look at drug kinetics and dynamics. What is drug kinetics? Another word for it is pharmacokinetics. Pharmacokinetics or drug kinetics refers to the study of drug deposition. It refers to the study of drug deposition. And it examines how the drug is absorbed, distributed, metabolized, and excreted from the body. So, the combined word pharmacokinetics simply involve the drug intake, its metabolism, and excretion from the body. Now, this figure 1, is a visual representation of what the body does to drug. That is, when the body receives drug, it absorbs it to the bloodstream, then it can distribute it to the tissues, metabolize it to produce the various metabolites of the drug, and then proceed to eliminate the remnants. Now, drug dynamics. Another word for it is pharmacodynamics. That is, drug action. What drug does to the body. Now, we just saw what the body does to drug. Now, we are looking at what drug does to the body. Now, what does it refer to? It is the relationship between drug concentration at the site of action and the resulting effect. Take note, relationship between drug concentration at the site of action and the resulting effect. That is, concentration and effect, including the time course and intensity of therapeutics and adverse effects of the drug. Now, this is another figure that depicts the relationship between drug concentration and effect. What you see here is in this drug effect relationship is a sigmoidal or dose response curve. As you can see, there are three phases in this curve. We have the subtherapeutic phase, the therapeutic or exponential phase, and the saturation phase. Now let's look at the three distinct phases. The subtherapeutic phase is the baseline. Now at that phase, the drug concentration is low, so there is minimal or no observable effect. That is, when you start taking drug, for instance, over a course of time, assuming you start the drug today, the effect of that drug will not be pronounced. It will not be felt somehow. The reason is that the administered dose is not yet sufficient to elicit a significant biological response. But as you keep increasing the dosage as prescribed, you will start seeing the effects. That takes us to the second phase. But the characteristic of this curve is that it remains relatively flat, indicating negligible changes in effect despite increasing doses. Now, the therapeutic phase. As the drug concentration begins to increase beyond a certain threshold, a noticeable biological response is observed. In this phase, small increments in dose lead to a substantial increases in effect, representing the optimal therapeutic range. The curve rises steeply, reflecting the heightened sensitivity of the system to the drug. Still on the relationship between drug and concentration and effects. We now talk about the saturation phase. The description is that at high drug concentration, the effect reaches a maximum plateau. Further increases in dose do not result in any significant enhancement of the therapeutic effect, as the system's receptor or pathway are fully engaged or saturated by the drug. At this point, the curve levels up, indicating that the maximum effect has been achieved. Now, let's look at concepts in drug concentration effect relationship. In this consideration, we often mention the leader dose, LD50, LD50 leader dose. This is the dose of drug that causes death in 50% of the subjects. Median effective concentration, EC50. This is the concentration of drug which produces 50% of its maximum effect. So LD50, EC50, and maximum effective dose, Emax. Again, this is the highest effect a drug can achieve, beyond which increasing the concentration does not enhance any response. So we have LD50, EC50, and Emax. Still on the concept of concentration effect relationship, we talk of therapeutic index, TI, as the ratio that compares the blood concentration at which a drug becomes toxic to the concentration at which the drug is effective. Mathematically, therapeutic index is calculated as LD50 divided by ED50. Remember, it is a ratio. The smaller the TI, the more effective or potent the drug will be. Now, therapeutic window. When you hear of therapeutic window, it refers to the range between the minimum effective concentration and the minimum toxic concentration, where the drug is both effective and safe. Other words are potency, which is used to mean the amount of drug needed to produce a given effect. Lower concentration produces higher potency. That is, drugs that are taken in very small concentration produce are very potent. The next word is efficacy. Efficacy is the maximum effect a drug can achieve regardless of the dose. Now, on the basis of drug interaction with the organs or tissues or cellular components, as the case may be, drugs are categorized as structurally specific drug and non-structurally specific drug. What do we mean by these terms? Now, for structurally specific drugs, they have unique properties in that their activity results from interaction of drug molecules and targets. Drug molecules and targets both have defined three-dimensional structures. That is, the drug have its own unique three-dimensional structure, and the target have its own peculiar three-dimensional shape. They produces effects at small concentrations. Minor changes in structure will produce major effects on activity. Most importantly, they show stereoselectivity. Now, this diagram demonstrates clearly the concept of structurally specific drugs. Now, we can assume the drug to be the key, while the target tissue as the lock. The lock will require the precise key to unlock it. Any deviation from the key will not produce the required effect on the lock. Once the key fits into the lock, of course, it will induce some activity that will unlock the key. Now, let's look at the characteristics of non-structurally specific drugs. The actions of the drugs are not related to their three-dimensional structures. Of course, that is why they are referred to as non-structurally specific drugs. Their structure does not determine their functions. The drug molecules and targets have both defined three-dimensional structures, that's for sure. The drug have its own three-dimensional structure. The target have its own three-dimensional structure. But both of them do not depend on each other like the structurally specific drugs. The activity of these drugs are due to their similar lipophilic properties. Now, below you can see the structure of chloroform, ethanol, acetone, and diethyl ether. Now, this structure of these compounds are dissimilar, but they have similar properties in that they are able to permeate the lipid membrane and execute their functions. We now look at bonding in drug reactions. The complementary structures of drug target produces various chemical bonds, such as covalent bond, hydrogen bond, coordinate bond, van der Waals forces, and steric hindrances. Of these bonds, three are of importance to us as students of biochemical pharmacology. These three are covalent bond, hydrogen bond, and steric hindrances. Now, covalent bond is an unusual bond formation in drug target interaction. This is because it is a very strong bond with high energy value. It is a bond of no significance in therapeutics, but desirable in toxicology. It is this bond that is formed in the alkylation of DNA by some cytotoxic drugs. Hydrogen bond, on the other hand, is a weak bond of enormous biochemical importance. It is formed by an electrostatic attraction between a protein and an unshared electron pair. It is this bond that determines the shape of proteins and nucleic acids. Now, steric hindrance is another important occurrence in drug chemistry. It is a term used to refer to the substitution of a bulk group or the obscuring of a functional group close to a critical part of the chemical molecule or enzyme active site. Theories of drug actions. Now, what principle determines drug actions? There are 5 principles proposed to provide a theoretical basis for drug actions. These principles are receptor occupancy theory with limitations, the rate theory, induced fit theory, macromolecular perturbation theory, and activation aggregation theory. Now we shall consider each of these in turns, starting with receptor occupancy. Now this theory, receptor occupancy theory, describes the relationship between the drug concentration and products of biological action. Now, this theory proposes a two-state model as illustrated in the diagram shown here. In the absence of a ligand, the receptor exists as in an inactive state, while the binding of a ligand activates the receptor. How does that lead to biological function? The diagram here, you can see the degree of drug combination with receptor lead to a drug receptor complex or a receptor drug complex. That molecule now activates a second messenger. The second messenger in turn activates an effector molecule which produces the functional effects. The second theory is the rate theory. This theory is based on the assumption that excitation of a receptor by a stimulant drug is proportional to the rate of drug receptor combination, rather than the proportion of receptors occupied by the drug as proposed by the receptor occupancy theory. Now, what are the properties of the rate theory? Look at the reaction displayed here. First, forward reaction K1, backward reaction K2. And the reaction, the equilibrium constant is K1 over K2. K1 describes the association rate constant. K2, dissociation rate constant. The ratio K2, K1, which is the equilibrium constant, corresponds to the reciprocal of the affinity. The value of Ke, therefore, determines potency of the drug. The induced fit theory. This postulates that the receptor need not necessarily exist in the appropriate conformation required to bind the drug. As the drug approaches the receptor, a conformational change is induced, which orients the essential binding site to the drug. Now, macromolecular perturbation theory. In this theory, a drug with a receptor interaction may result in two general types of macromolecular perturbations. First, a specific conformational perturbation that makes possible the binding of certain molecule that produces a biological response. That molecule we refer to as agonist. Secondly, a non-specific conformational perturbation which accommodates other type of molecules that do not elicit response. That type of molecules, again, is referred to as antagonists. So, agonist produces a biological response. Antagonists do not elicit any response. If the drug contributes to both macromolecular perturbations, that is, agonist and antagonist, a mixture of two complexes will result in a partial agonist. This theory offers a basis for the rationalization of molecular phenomena that involve receptors. The activation aggregation theory. This theory holds that the receptor is in a dynamic state or dynamic equilibrium and exists in a two-state model as activated form RO and inactive form TO. Now let's look at classifications and nomenclatures of drug. Classifications and nomenclature of drugs. Drugs are classified on the basis of action site and outcome factors. Now, on the basis of action site, the table below give a clear definitions and the names of drugs. First of all, we have drug affecting the central nervous system. They are referred to as called as CNS drug. That is, the drug that acts on the central nervous system. They are referred to as CNS drugs. Drugs affecting the heart, we refer to them as cardiovascular system drugs. For those affecting the blood vessels, they are blood-related drugs. Drugs affecting muscles are generally called muscular system drugs. For those affecting the gastrointestinal tract, they are referred to as the digestive system drugs, and so on and so forth. For example, those that affect the kidney, they are renal drugs. The reproductive system drugs. Those that affect the glands, endocrine drugs. Those that affect histamine were referred to as antihistamine drugs. Now, other outcome factors include anesthetics. These are drugs that are used to temporarily arrest the nerve cells. Analgesics, agents used to relieve pains. Narcotics, used to affect the mood or behaviors. Sedatives, There are hypnotic drugs, anti-Parkinson's disease, or anti-Parkinson's drugs. They are used to calm the nerves or reduce shivering. There are also drugs used to reduce spasms, as in the case of anti-epileptic drugs. Now, let's take one or two questions, perhaps a third. With this lecture, you can now construct between drug kinetics and drug dynamics. Secondly, you can now explain structurally and non-structural nature of drugs and give the types of chemical bonds prevalent with them. Number three, you can give the basis for drug classification, citing example with CNS drugs. The reference text, you consult page 1 to 16 and read it conscientiously. If you have any question, put it down till when we see physically to discuss the issues that bothers you on this topic. Thank you.